Hey class, good morning. This is Mr. Bean for AP Physics. This is going to be Unit 4, Video 43, discussing essentials of gravitational potential energy. So we'll be looking at pages 13 through 16 through the study guide. All right, so without further ado, we'll go ahead and start here. And we want to read a little bit about, you should be, take a close look at this, make sure you read this and we understand a little bit about gravitational potential energy. Okay, and now the only thing that I would say about this is that this is when we're so the formula here for gravitational potential energy, which is expressed right here. The only stipulation is when we're close, right? Close to Earth's surface. Earth's Earth's surface. Okay, probably let's when we mean close, we mean like 10 meters or so. Okay, close to Earth's surface. Okay, that's the stipulation here because G, remember G is the gravitational uh, is the acceleration due to gravity, and remember G is based on what, big G, right? The mass of the Earth plus the radius squared. So this radius is assuming it's the radius of the Earth. We're not going to go like 100 kilometers in the atmosphere. If that, then G is altered. So this is assuming we're close to the Earth's surface. So this G is used in here. So we can only use this for accuracy when we're close to the Earth's surface. If not, we have to use another form of this, which is beyond the scope of this class. All right, so make sure we go ahead and take a look at this and kind of read what's going on here, and then we'll proceed with 5.21. Okay, all right, so here is 5.21. Go ahead and take a look at the diagram here. And it says the diagram below represents a 155 Newton box on a ramp. Applied force causes the box to rise from point A to point B. Okay, what is the total amount of gravitational potential energy gained by the box? All right, so look at this. We have the hypotenuse, we have this distance, we have this distance. Okay, the only thing that matters, remember now, I'm going to give you a hint here. Uh, Gravitational potential energy, right, is equal to the mass, equals to the mass of the box here times G. And I'm going to go ahead and do this here. Now, what was it up here? They had Y, right? So we're going to have the final Y position minus the initial Y position. So when I look at this here, I'm not concerned about the 5.6. I mean, it's important, but I'll go ahead and we're not concerned about that. I'm not concerned about that. I am concerned about this because this is delta y. So it only matters is from this height to this height. Okay, and so this is my initial position. This is my final position. So this information is not needed in this particular problem. So go ahead and work on this problem here and see what you get. We'll go ahead and hit pause. Okay. All right. So 5.22. Which situation describes a system with decreasing gravitational potential energy? Okay. Take a look at the answers here and see which one. It could be more than one, but we'll see which one here. Uh, Take a look at that and remember, so to help you guide you with your thinking, just remember potential energy, gravitational, right, is equal to mg delta y. So delta y is the key here. So look at the answers here and see which one is delta y. Okay, we'll hit pause. All right. 5.23, which is the energy or the SI unit for energy in its expanded form. All right, so I'll give you a little hint here. So this is joules, right? And joules is composed of Newton times meter. Okay, and so we should know what the units of newtons are, right? Newtons are kilograms, right? Meters, see, meters per second squared, right? And then we have meters over here. So I'll let you finish this off and see which one of these follows is the correct answer. And we'll hit pause. Okay. Okay, 5.24. Okay, a car travels at constant speed v. So if we do that, what do we know about the acceleration? It is 0. Okay, a car travels at constant speed up a hill from point A to point B, as shown in the diagram below. As the car travels from A to B, what's happening to its gravitational potential energy? Okay, okay. So as of gravitational potential energy, so what's happening to it? So is it increasing as kinetic energy decreases, or increases as kinetic energy remains the same, remains the same as kinetic energy decreases, or does it remain the same as kinetic energy remains the same? Okay, so go ahead and hit pause, and then after the Ed Puzzle question, I'll give some commentary. All right. Some commentary here. Okay, the car travels from A to B. The gravitational potential energy is increasing, right? Because we do have a delta Y here for sure. Okay, there is a delta Y. Okay, there's a delta Y here. Okay, but it says here the constant speed. So take a look here. The gravitational potential energy is increasing. Kinetic energy decreasing? No, it's staying. Okay, constant speed means kinetic energy is remaining the same. So it looks like it's going to be choice B here. Okay. All right. We'll go ahead and go down to 5.25. Okay. Take a look at this problem here. An object is thrown vertically upward. Okay. So you have an object here, and it's going upwards like this. Okay. And which paragraphs best represent the object's kinetic energy and gravitational potential energy as a function of its displacement? Okay, so looks like here, what's going to happen here? So it's going to have some initial velocity. So okay, up here, final velocity is going to be 0. Here, initial velocity is not 0. Okay, it is not 0. Okay, so definitely there is some kinetic energy. So kinetic energy is not 0. Okay, but the potential energy gravitational is 0. Right up here, kinetic energy is 0. Okay, we should say initial kinetic energy. Okay, initial kinetic energy, and up here is 0, and the gravitational potential energy is definitely not 0. So using this to guide you, which one of these graphs kind of explain what's going on here? Okay, we'll hit pause. Okay, next one here, 5.26. While riding a chairlift, right, a 55 kilogram snowboarder is raised a vertical distance of 3.70 meters. So that tells me that delta Y immediately is 370 meters. Okay, all right. And we do have the mass, right? We do have the mass here. What is the total change in the snowboarder's gravitational potential energy? Okay, so there's going to be an increase. So what all that means is that what's delta U? Okay, changing. Okay, and that's going to be based on the okay, mass is not changing, G is not changing, but there is a change in delta Y. Okay, because he's raised a vertical distance of 3.7 meters, so this should be a straightforward computation here. Okay, that should be gravitational here. All right, 5.27. Okay, we'll hit pause. All right, so here we have this pendulum here, and it's being displaced, right? So this is length L, right? Now, let's take a look at this here. I'm going to go ahead and use a different color. Let's go ahead and use red here. And I'm going to go ahead and kind of go like this here. Okay, so this line right here, here's theta here. And this is going to be, now perspective is important. So we're going to kind of draw, this is our friend Joe. Joe's going to be right here. Okay, this is from Joe's perspective. We'll say Joe. Okay, so this is Joe's perspective right here. Okay, all right, and let's go ahead and kind of let's use a different. Let's use maybe blue here. All right, so from Joe's perspective, if this is L, then what's this here? Okay, so this length here is going to be L cosine of theta, right? L cosine of theta. Okay, and let's make it bigger L here. And this here is going to be L sine of theta, right? L sine of theta. Okay, now this is the part that we have to, this is the important part. Okay, so as a pendulum goes back and forth, what is L? How far is this off the ground with respect to this? So when we look at that, if I kind of draw a line like right here, isn't this really delta y here? This position, when it swings back up to here, from here to here is delta y. So a key question is, how do I express delta y in terms of cosine and so on and so forth? So how we do that is this. Delta y is simply going to be the length L minus L cosine of theta. Okay, that's going to be delta y. And then if I do a little bit more math here, I can factor out the L, and I can have here 1 minus cosine of theta. So this is how we can find height for a pendulum system. If we're not given delta y directly, we can do it in terms of L and theta. So what happens then is that I'll let you finish this problem off. So given this relationship here, what will be the expression for the potential energy gravitational for a pendulum system? So this will be a multiple choice situation, and we'll want you to go ahead and answer that. All right, and that will conclude this video.